Good morning, everyone. We have two speakers here again today for this session. So our first speaker is Mitali Banerjee from EPFL, and she'll be talking about some interesting superconductivity measurements in twisted trilayer graphene.
Okay. So first of all, I want to thank the organizers. Should I wait until TVR comes or I can start? Yeah. So maybe I just wanted to say that I feel really honored that you guys put me in the list with such amazing speakers. I kind of learned something since yesterday. And what I'm going to present here today is that my lab is only 6 years old now. With Corona coming, it's less than that. So bear with me. I will be just sharing some data from our group. And we are just trying to put things together and, like climb up the stairs. So I will be mostly talking about twisted trilayer graphene and why so. I will be going across this outline, namely why we were motivated particularly to do twisted trilayer graphene, and what did we observe in our magic angle twisted trilayer graphene beyond whatever already was seen, because this field is kind of every day you see new stuff coming up. And then we also found out certain displacement field dependence that I don't fully understand. Rather, we are still working. Sid is here. He's helping us to understand our data. And then finally, we also went to change the angle between the two layers so we can also go into the other place of the phase space. And finally, I will just conclude. So as these slides were shown over and over with the previous two lecturers, but then the point that I took here is that everyone is presenting the same fact, but maybe with different viewpoints. So I will show you the boring same slide where we are twisting two layers of graphene. And what happens is that because the moire pushes this AA and ABs farther, and that's the length scale we are talking about, and then we can go to the first Brillouin zone. And then finally, what happens is that we are left with flat band. And now why with flat band? Because my background was not really doing superconductivity, but the reason I took interest in superconductivity because not just this field is giving us a plethora of exciting physics, but somehow in flat band getting superconductivity is not so trivial. Because if we talk about superfluid stiffness, we know that it is inversely proportional to effective mass. And effective mass, if it's infinite, I don't know how to think of superconductivity. That means that this is a system where we can talk about electron-electron correlations, and that's what we will do. Hence, this is the bare minimum information that I took from these figures for you. Anyhow, as physicists, we are interested in as many knobs as we can turn on and off. So in twisted bilayer graphene, the thing was that electric field was not doing much because it's somehow there are two layers of graphene. You use either of the gates, it's kind of does the same thing. And in this case, what we have seen in twisted bilayer graphene, that superconductivity that was first reported, then ferromagnetism, then Pomeranchuk effect, and whatnot. But the tuning parameter of the displacement field was not really present in this system. Hence, we moved to the next one possible. This is twisted trilayer graphene. So it's pretty much the same as twisted bilayer graphene, but when you twist these two layers of graphene, 3 layers of graphene next to each other in opposite angles, somehow the band structure looks like this. And as you can see here very simply, that the electric field now has some effect. Namely, I can tune and I can hybridize the Dirac and the electrons, flat band electrons. And that's what makes it more interesting. So it's a gate tunable structure. And people before we jumped into this field have already from MIT and Harvard showed that the superconductivity here is more robust and the TC were higher. But now I know with improved TBG systems, every TC that we know of is kind of 2.5 Kelvin. So it's no surprise. And the superconductivity and correlated states are tunable is what makes our life easy. But not only this, there are some papers that motivated us even more, one of which is this reentrant superconducting state, which is really not so simple to found in every superconducting materials that you have, then superconducting diode and whatnot about other states too. So there's a versatile platform now, gate tunable and also electric field tunable. That's what we have in our hand. So why we are calling this unconventional superconductivity, as I just said, that superconductivity cannot be so trivial for if it's a flat band. And people have already found strange metal here, nodal gap here, pseudo gap here, nematicity, rain-trans superconductor. So you see the list is too long and too big. I'm not going to continue all of this. But still the order parameter of the superconducting states are not found. The relation between the correlated states and S superconductors are not really so much clear. The role of electron-phonon interaction is still debated. So it's not that we know everything. And the list can go on and on if we go to other states. So first of all, so I'm an experimentalist. I'm not going to show you any Hamiltonian, but rather a bunch of plots. If you get bored, just bear with me because it's just 30 minutes, okay? So the first plot I want to show, we call them fan diagram, namely the resistance as a function of magnetic field and the filling factors, as I said, that these are flat bands with 4 degeneracies. So you can see filling factors are 1, 2, 3, 4. So these are the full fillings. Anyway, our fan diagram is showing you that the fans are coming out of every correlated state that you would like them to be. So the sample was pretty homogeneous and good, but if I talk to Frank Opens or Dmitry Basov, they will say that the samples are only so homogeneous because the twist angle can have some inhomogeneity, okay? So within that framework, all I can say as somebody measuring transport, the sample was pretty good enough. We found the magic angle, this sample to be magic angle, and the fan diagram agrees very well with the previous reports from other big groups from across the pond. So there are certain things that we looked in our double dome system is that there are gap or Dirac where the Hall density switches sign like this. Then there is something called reset, and then there is something Van Hove singularity. In our sample, we saw all 3 of them. So you can see here, we saw in the full filling and the Dirac, we saw that the gap behavior. We also saw some resets near to the these filling factors, integer filling factors. And then we also saw some Van Hove singularity where we were expecting them or also seen before. Anyway, then we just simply go to superconducting state because this was our interest in this particular system. And as you can see that we saw superconductivity in both electron and hole, but for some reason in the systems, the superconductivity is more often stronger on hole side. And this is some typical measurement we experimentalists do in order to really prove that this resistance basically, becomes non-vanishing or non-zero when you put some magnetic field, just to prove that this is superconducting state. So the next thing, what we were interested in is the temperature dependence. And you can see with if you have some kind feelings towards the data that indeed the superconductivity is getting suppressed near a filling factor which is close to 2.6. And what we did is that we took the temperature dependence on either side, and you can see again that the one that is on the right side, that's the red curve, is kind of have a straight, this is like a straight line in a way, you can see it's linear, and then it jumps down like a normal superconducting state that you are aware of. But when it comes to this side of the dome, the resistivity somehow has some convex feature here, which is not fully linear. And that's something that I want you guys to remember when I will try to convince you that maybe these two domes are actually not having the same origin for the superconducting state. So this is where I didn't put it here, but it's somewhere close to this one. Yeah. And so the right dome is, the normal state is linear in temperature, and the left dome is way more like, the transition is less sharper than the previous one. So then we also put magnetic field, and in the magnetic field, you can also see that basically the same superconducting state is actually now developing something in between, which can be a charge density wave or something like that. But this is what we see in terms of that. So if you take a line cut, again, you see that as you increase and you put some magnetic field that destroys the superconductivity, specifically close to 2.6. This is what we call the, like the new star or something that is critical for us. So the left and right dome share similar maximum critical field though, but somehow they are not similar. But with transport, we cannot go beyond. So the other thing that we could do is that we can also do, this bias current dependence. And if you see in right and left dome, you will see that there is also striking difference. While the right dome looks like a normal superconductor that you will expect to have a hysteresis because there can be some heating effect. And the left dome, you can think of some quasiparticles that are there that basically is dissipating the heat, and hence they are overlapping with each other when we go back and forth. So there is no. And we have found this, that when these devices are very good, so we see superconductivity in every twisted trilayer we make, doesn't matter which angle, between 1.3T to 1.6. But when we are in magic angle only, then we see this kind of behavior. So you really need some high quality device. Yeah, this is for sure. And then the most interesting thing that we found, because you see, I told you that we are interested in tuning things. So we want to really have some electric field dependence. So now you see that if I turn on a small magnetic field, which is here 100 millitesla, we could start seeing that indeed the superconductivity has two domes in only a small window. Okay, so it's a very small window where we see that. And this is not something that is, like very trivial for us. At least we found a knob. So this is what we want to stress upon. That we do see double dome, but I must mention here that people before us from Caltech and from MIT, they already suggested through their data that there was some hint, but nobody actually showed this clear, evidence of this double dome. So we were the first to do this, yes. Yeah. So yes. So basically, what happens for the hysteresis part, that if you smoothly go, so I did put this 2D plot here. So you see in between here you don't have this. So in here you have the hysteresis. Here you don't have at all, and in between it kind of goes through this. Like after 2.4, we stop seeing the hysteresis. And of course, depending on the quality of the sample, how good hysteresis you see, this for sure. Like I have another device where the hysteresis was not as wide, but it was there. But it is always kind of stopping here. Yeah. Ask Sid. I'm going to show something he calculated. I don't know. I was initially very hooked to the fact that it's 2.6. So I was thinking 2/3 fraction, something like fractional filling of the flat band. But I'm not sure. Yeah. No. I have all data. I showed you. No, it's -2. Here you can see, I can show you here. So it's not really, we didn't see much, yeah. Sorry for going back. Yeah, so basically trying to show you that, what are we tuning after all? It's the band structure, right? So at low displacement field, we see one dome. And you can also see that, the Dirac electrons here. Then in between, in this displacement field, we see this double dome. I don't think I can see the Dirac clearly, but definitely there is no more Dirac left. And you see again one dome superconductivity. So that's what we have experimentally seen. And then, of course, we went to Sid and Steve for their calculation. If you need more information, yes. No, so the thing is that we did in-plane field measurement because Pablo already did, and that was the reason we went to Schonenberger's lab, but we didn't see any signature that was strikingly different. We have data. If you want, I can show you. Sorry? No. Because it was like more than 9 Tesla, and we burnt our device when we were in Nijmegen. Yeah, this is one thing, yes. So, okay, so offline, I don't know, but I can tell you that last year in APS, I was talking to Pablo's students. They said they see it in their samples. We didn't see in any of our samples. But I also talked to Yuan, the first author of that paper, because we were trying to look at it in our lab. In one of our TBG, we saw 3 of them, but then we found out that because these 3-axis magnets, you cannot push them to very high magnetic field if you use 3 of them together. So you always use only 2 axes. Hence, there is always some chance, something if left, then yeah, then what you see is, I think, so we have data with 3 reentrant superconductor in TBG, but then we calculated from the Hall, it was a very small angle. Yeah, so this is what I also want to say as an experimentalist. Okay, about the theory part, I can say that I would rather ask you to talk to Sid here because he's here, but I can just summarize that the possible superconducting pair states in the 2 domes that the right dome admits pairing between electrons with same and opposite effective spins, but the left dome only admits pairing between electrons of the same effective field. And also you can see here, there is also a wedge that they found in their theoretical calculation. And with this, I want to really conclude what we have seen in our double dome, in our samples. So we can tell you that our work also puts twisted trilayer graphene in this double dome community. That doesn't mean that I'm inferring here that we are solving some problems that were not solved in these communities. No, it's just that one more system that shows similar kind of behavior. And do the double dome share the same origin, or the order parameter is the question that currently in our lab we are trying to answer, because that's what we are interested in. Because our guess is that the 2 superconductivity has origins in the 2 related, adjacent correlated states like 2 and 3. And why does the double dome superconductivity appears only in a small displacement field window? That I think it's all about band structure. But these are the 2 questions currently we are trying to have some Josephson junctions and stuff like that. And we are trying to look at those things. Anyway, with this, I will go to the next set of data where I want to, so far, yes.
Since you're moving on, can I ask a question?
Yes.
What does the theory say? Is there a phase transition between these 2 domes?
Yeah, yeah. You can take a mic.
Charge goes in. So I think that's in these small inset figures. What you see is that, between A and B, if you see that, it's one of these incommensurate calculus spiral states, but where the charge goes in is whether it goes into, if you like, there's some IKS type reconstruction, and then you can ask, do you polarize into the opposite spin species, or do you say in the same spin and populate the band that was, at every point there's a state that's orthogonal to the one you occupied? Do you do that? So that's the picture in between 4 and 5 in the insets, right? So there's some change in how the charge goes into the insulating state. That seems to be, I don't think I would say it's a sharp phase transition. It's some detail in what the unoccupied states at this mean field level are, right? So at mean field level, you just see everything just energy crossings, right? There's not smooth transitions for any, these are all abrupt. So I don't know if there's sharper than that. It's some change in how the normal state is constituted. And then near -2, you see it's much simpler. One thing you can say is that at least this vertical line there is the difference between doping into the kind of fully filled band of -2 versus the IKS state of -3. They're sort of 2 different ones. So that at least has a rational explanation. You say one of them you're moving away from -3, and the other one you're moving away from 2, and that's vertical line. Yeah, in some, yeah, you guess.
Yes. Yeah. Yeah. that's what we are trying to now look at in another sample. Yeah, take a mic, please.
Pocket is like from the gamma point is emerging compared to -2 is like a cave.
Thanks, Sid. But yeah, I thought as you are here, better you answer the question rather than me trying to, woo people with. Yeah, sure. I have what's data? Sorry again.
So in fighting about re-entrance, do you see this Pauli limit violation?
It's in TPG. I have 3 domes. In PPG, no. We didn't see. We didn't see
the Pauli limit violation.
No, I didn't see. But I know that Paolo's student told me last year that they see in all samples. That's what they said.
But you don't see it.
Okay, for me, I don't have a parallel magnet like that. So I went to Nijmegen, we blew up the device. So, and whatever we tried in our lab, as I said, I have a vector magnet, but I cannot simultaneously use all the 3 of them. So I had to use only 2. And that's the reason I had the conversation with Yuan. He's a very nice boy. And he also said, he told me he also used 2. So the thing is, he's I must say, I'm very new to this community and people have been very kind and gracious towards me. So I learned from them. So, and he told me that he used 2, so I tried. But then from the hall, we found out that there was some angle. That's what I'm telling you. I'm just telling you as an experimentalist what I would do. Yeah, that's the thing. Because he has a 12-1-1 magnet, but he used 10 and 1 and not the 3rd one. And we had 9-1-1 and we were trying anyway. So that's what I'm saying.
Just one, so that original paper, they see this Pauli limit violation, right?
Yeah.
So for the 2 dome or remind, I forgot, only single dome. There is not 2 dome.
No, there was single dome. But in their earlier paper, in their first paper, they have the Ginsburg-Landau analysis. And if you see that there was some deep exactly in the same place as also Stefan of Caltech in their data. They were seeing features, but for STM community, we cannot blame them because they have only 1 gate. So, and for the rest of them, for the transport, I can show you tons of data that I have superconductivity in every twisted trilayer. It's like not a single trilayer we have that doesn't have superconductivity. But the problem is that if you don't have really good sample, you don't see all the features here. In these ones, yeah, I showed you the RxX of all of these, the first. Yeah, we didn't do that analysis at that time, yeah. The formology that he's talking about, yeah. But it's a good idea. Okay, so I will just switch my gear to the next slot of the thing is, so what we see here, that double dome superconductivity is only existing in a small displacement field window. And what does displacement field does? It's basically a direct consequence is a band structure manipulation, right? So there can be one thing that hybridization between the Dirac band and the flat band is the cause, or it can be the change of flat band width because we are doing, some modulation of the electric field, or other effect by displacement field, which I'm not aware of, okay? With this, we just go to, we are continuing because we blow up the other device, so we made new device. And as you can see that superconductivity again is pretty much nicely existing in either side. And the correlated state superconductivity can be tuned with the displacement field. And these are the data that people have already published. So we can see also that Dirac electrons coexist with the flat electrons, as you can see here. And then finally, we also show that, that the displacement, so there is basically the Dirac electrons are changing in the system as we are changing our displacement field. So there is a Liftis transition across the critical displacement field, and we call this displacement field as DC. Okay, so this is one of the critical displacement field that we talk about here. So we are just trying to see, how from the other data sets, how the displacement field is actually And this is, again, in a simple displacement field window. This is Rxx and Rxy. And then I'm just taking just line cuts, okay? So this one is at d equals to 0. And then in an intermediate d, you can see it's all of a sudden, some peak that pops up in the resistivity. While again, if I go to a higher displacement field, it becomes flat, okay? So the flat band width increase with the displacement field. This is some point that we are making here. And at a critical field, we are calling it DH, let's say, because these are Hall data. We are trying to, look at those. And for nu equals to -3 correlated state, it disappears with the Hall density switching from reset to VHS. So this is also something that in the filling factor 3, we try to notice. Okay, so this state disappears with Hall density switching from reset to Van Hove. And the last one is that basically that when we go to, -3, the correlated states of -3, we see that the Landau levels from mu equals to -3 gradually fades away as we increase the d. Okay, so, and we also see that the right dome is like in a low displacement field, only the right dome, then there is double dome, then there is effectively one left dome there. And the superconductivity is tunable by displacement field with double dome only in the intermediate window. So we are still on the same path as the previous sample that we had. And as you can see that, that this is a feature that I already showed in the previous sample. But what we conclude from here is this, that there is a critical field when the Fermi volume of the Dirac band totally disappears and a Lipschitz transition exists. Then there is this displacement field where the correlated states nu equals to -3 disappears and the Hall density changes from reset to Van Hove singularity. And then there is a displacement field when the double dome superconductivity starts appearing. Okay, so these are these 3 displacement fields. Currently, in our lab, we are trying to see how to correlate them so that we are measuring some samples to make this story forward. And are very, very close to each other, That's the thing. All these displacement fields that I showed you, they are actually pretty close, like if you look at those numbers. No, it's just 3 different measurements that we are trying to, because we are looking into superconductivity, we are looking into nu equals to -3, we are looking into, like the Hall density and stuff like that. We're just trying to make, like, from Fermi surface and everything, how to kind of wind this up if we can really understand why this double dome superconductivity. They're similar, yeah, they're very much same, yeah, exactly. So far, this is where the double dome stops, and I will finish in 5 minutes. The next stage is like, what happens though? So this magic angle twisted trilayer is when you have 2 layers in angle theta, and then the third layer is with minus theta. So this is the magic angle theta that is alternate theta minus theta situation. We were also asking this question that once we stamped upon a device that we liked very much, we tried to understand, of course, that how does it go when these are the 2 different thetas? So again, we are not the first to think about all these things. People have actually measured and showed this kind of supermoral lattice, and also there were some papers of quasi-crystals before us from MIT. So these are the STM measurements and STEM measurements to show supermoral lattice in this kind of situation. So now let's see, in case of transport phenomena, what will happen. Of course, Amir Yacobi was before us. He published in Science. Our data have some resemblance with him and something new. So what we see is, first of all, as if you remember the few slides back, I showed you this magic angle sample where things were actually mirror symmetric. Here we don't have the mirror symmetry. That's the first thing, that this sample is actually different. So there's the asymmetric ND mapping. Then the superconducting state has many other insulating states that is coming into it. And we know that the two twist angles are different. So for the students, if you want to know how we try to understand that in the data, so you basically take your fan diagram and you look for the peaks, insulating peaks, and then you look for the periodicity. And this is how we found that one of the angle is like this and the other angle is like that. And the real, how do I say this, like serendipity or accident or whatever, the three papers that we know of when we were writing this paper, one was the quasi-crystal paper from MIT. That has also a difference of 0.5 degree. Amir Yacobi's work with STM also had the same difference of angle 0.5. And we were also 0.5, but all the three papers are basically showing some similarity and more dissimilarities. So why so? I don't know. All I can say that maybe because we were close to magic angle of bilayer TBG. That's the only thing I can argue with the reviewers. Anyway, so we also confirm it with Brown-Zach oscillation, which we were inspired by the Manchester people because they do this kind of stuff. Here also we kind of found that similar Moray length. So it was just confirming that we have two different thetas. So what does this can do? So we have a Moray and another Moray, and we have super Moray. So basically what it does, it dices the band that you have. And we could go over all the data, but I know that I'm not showing enough Hamiltonians and only plots after plots, so people should not fall asleep. But these are all the details from where we try to also get the density so that we can relate them. And then we found out that indeed everything was falling into place. We see Dirac, we see flat electrons and everything. So we also see here the dicing of the bands, which we were also seeing before us from Stanford. And then what we saw very interestingly is that somehow the strong interaction results in isospin symmetry broken states. So we see isospin symmetry broken states, which was very, very surprising for us. Don't ask me why, because I also don't know, but that's the observation. And we also see cascade of superconductor and insulating transition, but here now you know, it's just a superconducting dome that is being diced by all the insulating states that we have because of the supermoray. And the thing is that we were always, there are certain things that if you are interested, you can look into our paper in the archive. But the resistive states of the superconducting dome breaks them into smaller domes. And finally, all I can show you that the distance between the nearby insulators correspond by half filling of the supermoray lattice, which we don't know why. So what we did is like we experimentally just drew, it's literally my student drew it by his hand. He said that, okay, this is the picture we like it to happen, but this is also another picture that can happen. So it depends. So we have just two energy scales here, which is relevant. So one is interaction, and another is the supermoray. And we think that maybe this is what is happening, but yet I cannot tell you if this is true or not from the data. I cannot, but this is the model we had. And so I can conclude now, as I'm having only 1.5 minutes. No, I'm not rushing, but it's just data. If it provokes some thought, I will be more than happy, but I just don't want to keep just. Okay, so as I said, supermoray is just interference between two Moray lattices results in this supermoray lattice. And it's strongly altering the band structure. At least we can see them being diced. And the most interesting point for us was this isospin symmetry broken states and the superconductivity appear in the supermoray mini flat band. That means that we can really, this offers a platform to discover and design unexpected electronic quantum phases. And so what is the conclusion and outlook from this work? First of all, we showed some tunable double dome superconductivity, twisted trilayer graphene. We also show that there is some three critical displacement fields that are effectively important in magic angle twisted trilayer graphene, which may uncover the double dome nature. Of course, we are also going for other avenues. The problem is that we tried to do some noise thing, but the problem is that TBG has very high resistive states, but in PTG you don't have. So the junctions are, the JJ that we are trying, it's a bit difficult to do them. We observed also the existence of supermolar lattice in the mirror symmetry broken TTG. And my talk cannot be finished without thanking the kid that actually did all this work. So he's the student that, there's no paper in my lab that he's not there. And he was the youngest when he joined. He started his PhD with me when he was 22. He graduated this year when he was 26. And he's a very talented boy. The double dome has been already published, and we are waiting. The e-proof is done, this to be coming online next year. And with that, I will just say that in our lab, we believe that anyone can do. And I thank you for your attention. And if there are any questions, I will be more than happy to answer.
Yeah, questions?
So this unequal twist angles, you had this pictured orienters of θ12, θ23,
Yes.
straight line, which was the mirror symmetric case.
Yeah.
Yeah. So where, I mean, so you're living to the bottom of that straight line.
Yeah. Yeah.
So where are you relative to the Pablo's quasi-crystal?
So the thing is that in our case, our angles are 1.3 and 1.7, and I think Pablo is 1.4. We are pretty close, you know. That's the funny part.
It's 1.4.
1.4 something and 1.8 something like that.
It's not far away.
It's not far away. And when Pablo was in my lab and we were showing the data because we had to answer the referees something, so you understand, because they had some paper from MIT, and Pablo just said that just tell them you have better sample. He said just tell them. I said okay, so maybe I can write that Pablo said that our sample is better. But you know, like I think my main point will be here. Indeed, these samples are so inhomogeneous at times, you know, it's like, and students are making with their hands, right? So in this case, I don't want to really just pinpoint something here or there. It's just, I feel, if we dig enough, like I said, the twisted trilayer graphene, we dig a lot, and we see superconductivity everywhere. Like all the samples, you can see superconductor. It's just that we don't pursue all of them after maybe 2 or 3 days. That's the reason. Yes.
Measurements, is it pure DC technique or you're putting AC on top of it?
So this is lock-in, yeah.
So when you serve a hysteresis, shouldn't that depend on the amplitude?
We did it with DC. The hysteresis, yeah, we did it with DC.
Other question is, I mean, this thing is so rich, the entire systems. I'm wondering if, well, before that, are there vortices in these things?
I will like to believe that. That's why we are parsing all these things. What do you say, Sid?
What is the Ginsberg-Landau?
So Ginsberg-Landau is what Pablo did a lot of this analysis. You know, the correlation length, I think, the coherence length is kind of order of 30 or 40 nanometers, less than 50, if I remember correctly.
What is the penetration?
I think infinite, yeah.
Infinite.
Yeah.
So what are your device sizes? They're like 50, 60 micron.
It's 10.
So shouldn't things depend upon where the vortex nucleate? I mean,
You are absolutely right. And this is the reason I said that when we are making the samples by hand, you know, like there is always a possibility that there is some inhomogeneity of the angle locally. I think Abhay can talk about it because we always cite his paper of STM about this kind of stuff. So about the nucleation, you know, I don't know if that kind of domain to domain can have, you know, kind of help even that pinning of the vortices.
or
Okay, so all I can tell you that in our lab, we cool down multiple times the same sample and we end up seeing the same thing. So maybe I'm not cold enough. So our coldest fridge can go to, we say 12 because that's the fridge shows, but my anti-dot measurement tells me it's 100 millikelvin or 120 millikelvin. Like we measure some dot also, gallium arsenide and graphene. So we know that the temperature is, so I think the other people may have lower temperature and they can. So.
Curious. I mean, this thing is so rich. Possible that there is a superconducting phase with multiple phases and different frequencies there. How could you see?
So as I said, like I tried doing some Josephson junctions. We tried also doing some high frequency measurements in a squid form. But in those devices, we didn't see at that time double dome. As I said, like, we need very high quality device. So we are thinking of first to do some Josephson junctions and study unrev, reflection, etc. But I must tell you that I don't know. That's my problem, yes.
About either of the domes?
So as I showed you, the temperature dependence, if you remember. So for the left one, maybe I have to go pretty fast and pretty backward. So what we see is that the left dome is not really the normal superconductor to like the transition that you will expect, basically. It has some convex nature in the RT, but the range of the temperature is so small, I don't know what to say. So yeah, so you see the red one is the one from this side, which we think is the normal good superconducting state. But if you look at the blue, you have to be a bit kind maybe towards the data, but there is some convex behavior. And then as you can see that it kind of smoothly goes, it's not so abrupt. So we do think there is some quasiparticles there for sure. We would like to push the narrative that this superconductivity is somehow connected to this and this one is to this, but we are trying different mechanisms to address that. Yeah, not yet done. Yeah.
We'll have just one last question.
Yeah.
We are deprived here at the back of the lecture hall. No one ever asks us to ask a question. I wanted to, you've emphasized the transport properties of these systems and the work is extensive and remarkable. But you haven't mentioned to us to what extent you know, or the community knows about local moment behavior, entropy measurements. To what extent has that been done on trilayer graphene and what is known?
I can tell you that the entropy is something that Andrea does, and I'm not sure that trilayer has been done, but we are trying that too in our lab.
And is there any STM quantum dot-like behavior?
STM is done long back.
And is there, can you see Hubbard sidebands? Is there a sign of quantum?
So the first STM paper that came up in 2021 that has, or 2022, that has this V2 U shape, like namely this superconductor was something like, one was BEC-like and one was like a nodal superconductor. That's what the STM data initially said.
But I'm asking about whether theoretically there's good reason to believe that the band structure of this is not so different to that of bilayer graphene. And,
yeah.
And so what I wanted to know is what evidence is there for local moment formation in this system? And to what, that was my question. Maybe the theorists know answer
Abhay,
it.
do you have any comments about this? You are the STM person sitting here, so
I want to know to what extent there's signs of quantum dot behavior of local moment formation in the trilayer graphene system. As there's clear evidence for it in the bilayer system. I wanted to know to what extent it's here too. Sidebands?
Mike.
Sidebands?
As these cascades and sort of filled and unfilled whatever symmetry broken states.
Mhm.
and things that have been interpreted in terms of Coulomb-driven gaps.
Mhm.
But quantum dot, what do you mean quantum dot?
That's exactly what I mean, cascade.
Yeah, that's been seen.
Thank you.
The Dirac is there still, yeah.
I see. And perhaps one very small question. To what extent is there any evidence of strain splitting the bands, like there is in bilayer graphene? Yes, you know, there is this beautiful feature seen in the twist microscope, but you can also see it in the cascades, which seems to indicate a splitting of the bands from an 8-fold symmetry to a 4-fold symmetry.
Yeah.
Harold, thank you, thank you. Mm. Yeah. Okay, great.
Okay, in the interest of time, maybe we can move on to our next speaker.
Yes.
Let's thank Mitali one more time.
Thank
And if there are
you.
questions, please feel free to ask her later.